Hi, Eduardo.
Okay, so our speaker today is Owen, and he will speak about topological full groups by example. Please, Owen, go ahead.
Okay, so thank you very much again for the invitation. And so my name's Owen, if you haven't met me before, and I'm doing a PhD at the moment in Glasgow. And so the idea of this talk is really to give like an introduction to topological full groups. I know there's a couple of experts in topological full groups in the audience, so hopefully you get a little bit from my perspective on them even so. And it should be hopefully just quite a nice little broad overview of it. And I wanted to start off by saying that, so topological full groups, it's like quite a new field of study, and it's interdisciplinary. So there's very non-trivial things happening on the group theory side of things, and there's some non-trivial things going on the operator algebras and the sort of groupoids and things like that side of things. So I wanted to say that, you know, if you have any questions, and especially if you have any questions about the group theory side of things, like, please just stop me and ask. There is like enough time to ask me questions. I wanted to talk to you about this arrow to start off with. So I already mentioned that it's about the interactions between sort of things in operator algebras and things in group theory. And the first thing that I'd kind of like to point out about this arrow is that it's almost going in the opposite direction to how a lot of these interactions usually happen. So usually what happens, right, is we start with a group that we're interested in, and then we'll build a dynamical system out of it, or we'll build a C-star algebra out of it, or something like this. And topological full groups really work in the other direction. So what we're doing is we're starting with things like C-star algebras that we're interested in, or groupoids, or this kind of thing, and we build from it a group that is interesting for group theorists. So we present them with a nice present. And the other thing that I'll say about this slide is that you see that I have this sort of and or bit here. So I have, and the reason for this is that I'm imagining that there are people in the audience who are more comfortable thinking about things in terms of operators, because this is the NCG seminar, in which case you'll probably like to think about these as coming from Cartan subalgebras. There are people that will be more comfortable with dynamical systems, so like groups acting on spaces, and there'll be a definition of topological full groups for you, and there'll be a definition for people that are into groupoids as well. And it's just to say that I will give 3 equivalent definitions of a topological full group, and you should just pay attention to whichever one makes the most sense to you. Okay, so without any further ado, let us go for the first definition, which is in terms of a sort of Cartan subalgebras. So this is the C-star algebraic definition. Okay. So the setup is this. So you start off with a unital C-star algebra, just any C-star algebra with a unit, and it's going to have one of these Cartan subalgebras. So if you're not too sure what a Cartan subalgebra is, this might not be the place where you learn what a Cartan subalgebra is. But I think what's relevant for this definition is that this Cartan subalgebra is an abelian C-star algebra, and it's maximal inside A. So it's a subalgebra of A that's maximal and is abelian. And it's maximal, and it has some other properties that makes it very nice from the perspective of studying groupoid C-star algebras, but this is a whole different talk. Because it's an abelian subalgebra, we can talk about its spectrum, right? And what I would like is for its spectrum to just be the Cantor space, right? So it's the continuous functions on some locally compact Hausdorff space, and I choose that locally compact Hausdorff space to be a Cantor space. And I should say that there are many C-star algebras which have Cartan subalgebras like this. And we'll mention a couple of them. So yeah, so this talk is obviously by example, and hopefully we'll cover a couple of examples of C-star algebras that maybe people have seen and see how this works in practice. Okay, so the idea for a topological full group, we want to build a group out of these two sort of ingredients. And so how do we build a group out of a unital C-star algebra? Well, we consider its unitary operators, right? So we look at the unitary operators, but when we do this, we do not incorporate any information from this Cartan subalgebra. And I would like to incorporate some of this information. So instead of looking at all of the unitaries, this B, because it's a maximal abelian, is going to share its unit with A. And so I can look at the unitaries which normalize this Cartan subalgebra. And in that way, we can kind of think about them as acting on the Cantor space. So that's what I do. So I consider the unitary elements which normalize this Cartan subalgebra. But when I do that, I'm going to end up with a group that, whilst it contains a lot of interesting information, it's not particularly interesting from the perspective of group theory. And the reason why, right, is it contains all of the unitary elements inside this Cartan subalgebra. So it contains all of the maps from the Cantor space into the unit circle in the complex plane. And that's like an uncountable group, right? And it makes things very ugly. And so what we do, it's also a normal group, we can quotient out by that. And then what we're going to find is that we've defined some kind of infinite discrete group, actually. So the reason why it's called a topological full group, as opposed to like a full group or whatever, is because this is the topological, i.e. the C-star algebraic analog of what's been seen already and studied a lot in the measurable setting called a full group. So it's kind of a confusing name inherently, unfortunately, but these topological full groups are not topological groups, they're actually discrete groups. And we can consider the binary operation on this group to just be operator multiplication, okay? So that's the definition in terms of C-star algebras. If there are any questions about that, if not, I will go to the next slide. Okay, so the next slide is the definition in terms of a group action. So actually, when you have a discrete group acting on a Cantor space, you can build up one of these C-star algebras as a cross product, and we're going to have that it's got a Cartan subalgebra, which is exactly the continuous functions on the Cantor space sitting inside that discrete cross product. So that's kind of how this relates. And this definition, I think, looks a little bit confusing from the start. So I want the action to be topologically free. That's just, you know, regularity condition. But like the idea is that what we want to build is a group of homeomorphisms on this Cantor space. So this group is acting by homeomorphisms on the Cantor space that locally look like this action alpha, okay? And the way that works in practice is we have the following conditions. So for every point x in my unit space, so this diagram, this is representing an element of my topological full group, there's going to be some compact open neighborhood of x, which we call U here, and a group element such that our homeomorphism is acting like that group element on the compact open neighborhood. So over here, we have some point x and some compact open neighborhood, and our homeomorphism is going to be acting like alpha of g of x on there. And so the idea of this element is basically, what if you had a group element that took u inside v under this action phi, alpha, took v into w, and that could be another group element f, and w back into u. So you could have three different group elements. One takes u into v, one takes V into W, one takes W back to U, and you can piece them together to get a homeomorphism. And that's the idea of what these sort of group action topological full groups look like. So with Cartan subalgebras and with group actions, there's this sort of more general thing hiding behind, which is this thing called a groupoid. And I'm sure there'll be some people here that like groupoids. So this is the sort of more general definition. And you'll notice that I'm not using a lot of adjectives on my groupoid. So I've not, for instance, asked for my groupoid to be Hausdorff and things like that. So this one is more general, really, than the other two that I've given. And so the idea here is the space that you're acting on, the Cartan subalgebra. For groupoids, it's the unit space. So for groupoids, it's the unit space which I want to be a Cantor space. And I asked for this groupoid to be effective in a tau. So what these adjectives are giving me is, so the Talness condition, what this means is that I'm going to end up with a discrete group at the end of it. It also means that your topology of your groupoid is generated by these bisections, whatever they are. And the effectiveness is giving us that this is really going to be a group of homeomorphisms. And this is kind of the idea here. So the definition here is, so we're looking at the subsets of our groupoid. So our groupoid, we're thinking of like arrows on our unit space. So a collection of these arrows where all of their sources, so the union of all of their sources, or alternatively, the union of all of their ranges, is going to be the whole unit space. So it's going to be all of G0. And moreover, they're going to be these compact open bisections. So bisections means that it's actually, when we look at this collection of arrows, it's going to form a homeomorphism of our unit space. So just like how, hello.
One little question.
Of course.
So if you have say have a semigroup, inverse semigroup acting on a space, and you form the groupoid of germs, I think you can recover the semigroup as the associated semigroup of compact open bisections, right? So that this would be, this full group would be like a sub semigroup,
the unitary
semigroup that is a group.
Yes, exactly. So it's with this picture. So if you're thinking about your open bisections, they form an inverse semigroup acting on your unit space. Exactly. And one way to think about this group is that it's the subgroup of that inverse semigroup called the unitary subgroup. This is like a known thing. And so that unitary subgroup is the exactly as you say, the group of the inverse semigroup elements such that their source and their range is the whole, is the unit of the inverse semigroup. So that's one way to think about it from a more semigroups perspective as well. So there are many ways to think about this. Yeah, so where was I? So, and yeah, and I guess what's important, right, is that, so part of why people are interested in these topological full groups is that they would like for them to retain a lot of information about these groupoids, about these things and stuff like that. And the fact that my groupoid is a tau is going to give me that these bisections are going to give me all of the topological information that I want about my groupoid. So one definition of a tau is that your open bisections generate the topology. And the fact that my groupoid is effective means that basically I can think about my bisections as partial homeomorphisms, and I can do this without forgetting important information, getting important algebraic information. So this effectiveness assumption is basically saying that any bisection that acts like the identity is going to be a subset of the unit space. So that's one way to talk about effectiveness, actually. Okay, so those are the three definitions, and I'm hoping that everyone at least has some kind of idea in their mind of what a topological full group is for them in one of those three ways. So now I'm going to move on to why I think these guys are interesting, these topological full groups. So the big reason that people first started looking into them is because there were these, if we forget about the word topological, there were these full groups in the sort of von Neumann setting. And they were really influential in the theory of Cartan subalgebras and von Neumann algebras. And the reason why is because they were really good invariants, actually, of Cartan subalgebras. And so this theorem that I'm about to present, there's a very good analog of this in the von Neumann setting. And what this theorem is telling me is that under very, very minor assumptions on my groupoids, so actually more minor than what I had in my previous slide, in the sense that my unit space is now no longer just a Cantor space. It's like it can be non-compact, and there's still a definition that works, but this is beyond the scope of this talk. However, I am adding in that now my groupoid is minimal, and what this gives me is simplicity on the side of these groupoid C-star algebras. And the other thing is I've put in Hausdorff here, and the reason that I need this is because I would like to also phrase things about Cartan subalgebras, but this isn't strictly needed. And so the theorem goes as follows. So the theorem is that under these very minor assumptions, it's the same thing to say that the topological groupoids, these are tau groupoids, are conjugate, as it is to say that these topological full groups are isomorphic as abstract groups. So these topological full groups, they remember essentially all of the information, just as abstract groups of tau groupoids under these quite minor assumptions. And for people that work in C-star algebras, this should be exciting because it means that they are incredibly good invariants of these Cartan subalgebras. So these topological full groups, for instance, contain more information than the Elliott invariant. So that's like kind of an exciting thing in some ways. You could distinguish between two Cartan subalgebras in the same reduced groupoid C-star algebra using these topological full groups. But the big disclaimer here is you think, oh, wow, so there's this amazing invariant and all it is a group. But what I would say is that in many ways, I show this theorem sometimes to my friends in group theory, and they also think, wow, this is an amazing theorem. And the reason why is that, oh, I can tell apart these two amazing groups. And the only way I need to tell them apart is by looking at some C-star algebras or something. It's kind of like one of the grass is always greener on the other side type thing, where I would consider it a very hard thing to determine isomorphism between the two groups, these two groups, and also a very hard thing in general to determine an isomorphism between these Cartan pairs. But I would say that we maybe even have better methods on the level of these Cartan pairs. Certainly in my research, the way that I have distinguished these groups is by looking at the C-star algebras, actually.
Yes.
Okay, so yes.
So in the particular case, so say you have a finite graph that satisfies the known conditions that make it the C-star algebra simple.
Yes.
So in that case, I think that there is some theorem that says that the third condition holds if and only if the Bowen-Franks invariants are the same and some determinant has the same sign. So in that situation, what are the full groups?
Okay, so yeah, I can talk a little bit about this. One thing that I would say is that there have been real masters of this. So these two authors that I say here, Nyland and Ortega, they have written not one but two incredibly strong papers about the topological full groups of graph groupoids. And so these ones can be very strange in general, but one example will come up. So one of my examples that I'll present later is the Kuntz algebra. And I'll comment a little bit more about this for sort of general graph groupoids. But the spoiler is that they are very interesting from the perspective of group theory. So the spoiler is that very often these groups are simple and they have a finiteness property called type F infinity. And this is very strong. So this was a huge part of the motivation of why people wanted to understand topological full groups, is because they had already studied, I guess, the one coming from the Kuntz algebra, or coming from the graph on two
So that's to do with one of the Thomson groups or something.
Yes, exactly. So we really consider them as generalizations of Thomson's group V, if that means anything to you. Exactly. Yes. Okay, so what kind of groups? I've kind of given the spoiler already. So so in group theory, people have been interested since the start of group theory in simple groups, right? And in particular, simple finitely generated groups, because they're like the building blocks of other groups, right? And what I would say is, in modern times, we've realized that we've very much understand the case of finitely generated simple groups, right? You know, there's this full classification. Of course, there are questions and things like that. So it's kind of a natural question to start investigating the infinite finitely generated simple groups, right? And the first person to kind of say this was is anonymous, but was from a conference proceedings in back in 1890 or something, and they asked the question: is there a finitely generated simple group that's infinite? And this question was actually open for about 60 years. And there are examples, but they're really, really hard to generate. And I think this is something that really needs to be stressed in any introductory talk. So I'll just talk you through a really sort of naive approach, right? So I just think, if you think of a finitely generated simple group, the first thing that you'll think of is a finite simple group, right? But these are not going to be infinite. But more interestingly, you sort of have this case of anytime you're thinking of a finitely generated infinite group, you think of something like the cyclic group, which has tons of normal subgroups. It's very hard to just come up with off the top of your head one that's simple. And then if you're thinking about building an infinite simple group, the classical way that you would do this is you just take an inductive limit of finite simple groups, right? But if you do that, you're not going to end up with something that's finitely generated if it's infinite. So it's actually a really hard question. And what you need to find is a completely novel way of constructing groups. And so the first example was given almost 60 years after this question was asked by Higman in 1952. And this example by Higman is very good, but it's still I think, even open to write down the relations of Higman's group. So it's still not entirely like the best understood example. And since then, there have been sporadic things. So there's this Thompson's group V that's already come up. But there were also, like generalizations of Thompson's group V. But the thing is, there wasn't really a systematic way to build these sorts of groups. And that was until sort of topological full groups came along. And what's amazing about these groups is that when you look at their derived subgroups, so just a reminder for everyone what a derived subgroup is, it's the group generated by all the commutators of a group. You're often going to get something that's simple, infinite, and finitely generated. So, I mean, always these topological full groups are going to be infinite. I think I should have persuaded you of this by now, surely. The simplicity of these derived subgroups is actually characterized by minimality of your groupoids, or equivalently, it's like the simplicity of your reduced groupoid C-star algebra, something like this. Being finitely generated is still a mysterious property in some ways, but it's known that if your groupoid is expansive, which is this sort of dynamical property. So for the case of, say, group acting on a space, it means like being a subshift. So subshift-like groupoids, things like graph groupoids, you'll get that your topological full group's derived subgroup is finitely generated. And because of this, they've solved tons of open questions in group theory. So before topological full groups, it was an open question whether it was possible to find an infinite finitely generated simple group, which is also amenable. And this was closed by Jashenko and Monod in 2013. Then Nekrashevich came along, he did even better. So if you have intermediate growth, then you're definitely amenable still, right? But growth is only really defined for finitely generated groups, I suppose. So Nekrashevich was able to find simple groups of intermediate growth in 2018. Both of these very significant papers, like Annals papers. There was also a very nice Inventiones paper. So Skipper, Witzel, and Zaremski, what they showed was that you could get simple groups that have this finiteness property called type Fn, but not type Fn plus 1. And if you don't know what this means, so type F1 means finitely generated, type F2 means finitely presented, and type F3 is like even better still. So it's a way of phrasing being finitely generated and finitely presented in terms of topological data on your Cayley graph. And it basically means that the end skeleton of your Cayley graph is simply connected. What they found were things which were type Fn, so they had very strong finiteness properties, but they didn't have Fn plus 1. So they weren't, we call them type F infinity if they have all of these Fns. So this was a very, very significant result, another Inventiones paper. And then I'd say recently there's been some very significant progress around the Boone-Higman conjecture. So the Boone-Higman conjecture, for those who don't know, is one of these sort of guiding questions in combinatorial group theory. And the conjecture is that a group, so in combinatorial group theory, there's a theme of phrasing computability properties for groups in terms of what simple groups they embed into, right? And their idea is that every group should, with solvable word problem, should embed into a simple finitely presented group. And at the time of conjecturing this, every known example of a simple finitely presented group embedded into Thompson's group V. So they really needed a lot more examples of simple finitely presented groups. And now, because we have this realm of topological full groups, which even better we can use to almost blow up groups into these simple finitely presented groups. Because of this, it's been answered for hyperbolic groups, which are like one of the broadest classes of groups with solvable word problem. So that's a very significant result that I don't think it's quite out yet, but it's been communicated around. So, and that's by Blake, Belk, Matui, and Zaremski, and it should come out next week, I think. Okay, so without any further ado, we're going to go on to some examples because this has gotten all very abstract, and let's get it concrete. So let's start thinking about a concrete example. The first example that I'd like to focus on is actually the car algebra. So the car algebra is one of these UHF algebras, and it's going from the matrices 2 to the n to 2 to the n plus 1, and it takes A and it maps it to AO plus A. Whenever you have one of these sort of UHF algebras, it's actually true that you're going to get one of these nice Cartan subalgebras. And the way that you can build this is that, so Cartan subalgebras, what they really are is a generalization of the diagonal in matrix algebras. And if you look at this map, it's going to take a diagonal matrix and it's going to map it to another diagonal matrix. So you also get an inductive limit of these diagonals. When you get that, you're going to get one of these very nice Cartan subalgebras. And this Cartan subalgebra is going to have its spectrum also being, the Cantor space. So we can play this game and we can have a look at what its topological full group might look like. And it actually fits into this very nice framework of groups called interval exchange groups, which have been studied by many people now, people in dynamics, people in geometric group theory, for all kinds of reasons. So let me just explain the abstract setup, and then I'll tell you which one the car algebra is. So the input gamma is, you've got some subgroup of R with respect to addition. And what you're going to get is certain piecewise linear bijections of your unit interval. So your binary operation is just going to be composition of these mysterious bijections. And these bijections, the way that they work is they have to be piecewise linear. So and they're right continuous. And what they are is we're just adding something by our additive subgroup of R. That's actually just what we do. So we take it, and one way to think about this is that we take the interval and we slice it up at some points in gamma, and then we exchange it around. And that's why they're called interval exchange groups. Okay. And so I said the car algebra is one of these guys. So what group does this correspond to? Well, it's actually this dyadic integers. So z of a half, the ring generated by a half inside R. And that's going to be a locally finite group. It's actually true that the topological full groups associated with AF algebras are always locally finite. But yeah, so I found this example very interesting. One thing that I would say so some people have already said something about Thompson's group V. So you might notice that this is a subgroup of Thompson's group V, actually, just by this presentation. It's called the measure preserving subgroup of Thompson's group V. And it's part of this whole Zappa-Shep decomposition of Thompson's group V and things like this. So why am I interested in these interval exchange groups? Because I mean, this is not one of my triangle groups, right? This is like a locally finite group, so it's not finitely generated. Well, I'm interested in it because of this result by Zhishenko-Minot, where I was talking about this before. So what they asked is whether you can get one of these triangle groups, so simple, finitely generated, infinite groups, where it's also got this other finiteness property called amenability, right? And geometric group theorists, if you ask them, they really do think of amenability as a finiteness property. I should say this. And yeah, so their example, right, is also one of these interval exchange groups. And if you remember, it's the derived subgroups that are usually simple, not the whole of the topological full group. And it's the one where we choose as my gamma I'm going to choose it to just be Z O plus theta Z. So this theta being some irrational number, so like pi or something like that. So that's a subgroup of R, and then you can form the interval exchange group. You look at the derived subgroup, then GeNoCAS and Matui were able to tell us that it's a simple finitely generated amenable infinite group. And for people that are interested in what the dynamics are behind this, it's coming from one of these Sturmian subshifts, if that means anything to you.
Sorry,
yeah, so I got
question.
Yes.
This is any relation with something about unitaries in the irrational rotation algebra? Because this C plus zeta Z is the K0 group of the irrational rotation algebra.
Yeah, and so I can comment a little bit on this. So it's the C-star algebra associated with the Sturmian subshift. It's not actually the irrational rotation algebra. Something that I do is I compute the K-theory of all of these guys, and in particular for this guy. And what it turned out was, so K0 is like Z squared, and it's like ZO plus theta Z as an ordered group and stuff. But K1 was just Z. It's not Z squared, which is the irrational rotation algebra.
Right.
So it's not exactly the irrational rotation algebra, but this Sturmian subshift is very related. So it kind of comes from an irrational rotation, but it's a Cantor-minimal system, so it doesn't really come from. It doesn't give you the irrational rotation algebra. I wish it did. That would be amazing, but it unfortunately not.
Thank you.
Thank you. Good question, though. Okay, so yeah, so what have I done? Right, I'm a young researcher. I should talk a bit about my research. So I studied these interval exchange groups, and in particular, I studied them from the perspective of C-star algebras. So I was like, okay, so there's all of these amazing groups, and they've got these nice groupoids, and so they've got these nice C-star algebras associated to them. And so what I showed was that they're classifiable. So this is like in the sense of the Elliott classification program. So, you know, they're simple, they're nuclear, Z-stable. I guess Z-stable is the real hard part, often. And but they're classifiable in that sense. They're also classifiable in the sense that I can actually classify them, right? So part of the Elliott invariant, so I compute the Elliott invariant, is you have this trace pairing map, and it's going to give you some subset of R. Or equivalently, your K0 group is going to give you some ordered group. Anyway, these C-star algebras, their Elliott invariant is actually going to recover gamma as a subset of R. So what this means on the level of the groups, right, is that they're pairwise non-isomorphic. Because if the C-star algebras are different, then definitely the C-star algebras with their Cartan subalgebras are different. So I get a full classification of these groups through the Elliott invariant. I show that they're always different. So so in particular, it depends a lot on this theta. This is like which irrational number for this very interesting example. So you get two different groups if you start with pi z or ez, say. Anyway, and then I try and show try and investigate when they fit on this nice triangle that the group theorists are so interested in. So they are always simple, right? And one way that you can think about that is because the C-star algebras are classifiable, they have to be simple. Yeah, so the derived subgroups are always simple, but they're not always finitely generated, right? The car algebra one wasn't finitely generated, but the GeNoCAS and Matui one was. And what characterizes this finite generation is the finite generation of the underlying group. Okay. And I investigate the homology of these groups. So this classification gives you this nice corollary that there are more of these infinite finitely generated amenable simple groups than there are finite simple groups, right? Because there are uncountably many irrational numbers. Jushenko Minot already knew this, of course, but I think it's nice that you can see this using C-star algebras, using the Elliott classification program, I suppose. Cool. Okay, so that was my first example. Oh, and I forgot to say, we do not know everything about these groups. It's still open whether these interval exchange groups are always amenable. And we still do not know if there are ever finitely presented simple groups that are amenable and infinite. Yeah, both of these are hard questions, but I don't think I have too much time to dwell on why they're hard questions, but they are. Okay, my next example. So my next example is exactly the Kuntz algebra. So it's one of these, coming from one of these graph groupoids as before. So hopefully we all do know what the Kuntz algebra is. So it's got one of these Cartan subalgebras. It's actually got a lot of Cartan subalgebras, which give us a lot of interesting groups. Like different Cartan subalgebras that give us different interesting groups. And yeah, so this Cartan subalgebra, if you haven't seen it, it's like if you take some finite word in S1 and S2, and you look at the range projections of those words, that gives you a Cartan subalgebra whose spectrum is the Cantor space. And this comes from, yeah, the graph groupoid on the full shift on two generators, if you prefer the dynamical point of view. And what group do you get? Well, you get this group called Thompson's group V. And for the people that haven't seen it before, so this looks a little bit like one of my interval exchange groups, specifically the Carr algebra one, except I've got this steep slope now, right? And so what happens is it's the same setup. You've got certain bijections of the unit interval, and you want them to be right continuous and piecewise linear. But now they're of the form ax plus b, where a is 2 to the n for some n. So this slope could be like slope 2, say. And the b is one of these dyadic things. Yeah. So that's what Thompson's group V is. And why are people so excited about it? Why has everyone heard about it? Well, Thompson's group V was the first example of a simple finitely presented infinite group. And I mentioned that Higman's group was pretty hard to work with in practice. I would say that Thompson's group V was much easier to work with in practice. And there were many really beautiful generalizations of it and things like that. It was very significant for this Boone-Higman conjecture because, as I said, you know, it was the only real example of a simple finitely presented group up to embeddings at the time. It's been generalized in all kinds of interesting ways, and I'll talk a little bit about one of those ways in the next couple of slides. But yeah, so it's been called the chameleon group by Bryn. I don't know if people have heard this before, but it's because it shows up in so many different settings, right? So for us, we're interested in it because it's coming from the Kuntz algebra, which we're really interested in. But there's equally people in semi-groups, and they'll say, well, I'm interested in it because it's related to the bicyclic inverse monoid, this kind of thing. And another thing that I really want to stress about it is that it's even been a useful group in the context of like things like cryptography, like it's used in applied maths as well. I always think it's kind of interesting when in a pure maths talk you can say something about that. The reason for that is that like it's not a linear group, right? Because linear finitely generated simple groups are finite, but this is an infinite group. So we're just taking a look at the time. And so because it's not linear, but it does have a solvable word problem, so you can write an RSA encryption thing, it's very attractive from the point of view of cryptography. And actually, so are a lot of its generalizations. And then, so yeah, this final bullet point, it shows you that even though I say it's fairly easy to understand, we only recently computed the homology of Thompson's group V. And I find this a very interesting fact that the homology of V vanishes. So the homology of V is the same as the trivial group, like the group with just the identity. And the reason that I find this so interesting is because that's also what's interesting about the Kunz algebra, right? Because the Kunz algebra is the C-star algebra where the K-theory vanishes, yes? And it's actually true that these things are connected, and they're connected through a very beautiful paper that my supervisor, Xin Li, wrote last year, where he talks about how groupoid homology tells you some things about the homology of these topological full groups. And it's also known for quite some time that groupoid homology is very useful for K-theory in certain contexts. So this is Thompson's group V, this, my favorite group and all of this. But I wanted to try and understand some generalizations of Thompson's group V that were developed by this person called Melanie Stein. And what she did was she took this sort of definition and she said, okay, what's important here? So what you need is a group of positive slopes, right? So you just take some subgroup of the positive real with respect to multiplication, and that's going to be your slopes. And then you need your additive part to work well with that. So you just take the group ring generated by that group. And then what you consider is piecewise linear segments that have their slopes in this lambda and the additive part in this gamma. So these piecewise affine things. And instead of having it on an interval of length 1, you just have it on an interval of length L. And so this is very much looks like Thompson's group V. And you might say, well, how is this actually interesting in a different way? And one way that it's more interesting, I would say, is that so you can have irrational numbers, right? And when you have irrational numbers, what you're going to find is that your group ring is going to be, so especially if it's an algebraic number, your group ring is going to be a polycyclic group. And because of that, you're going to get things like an embedding of, for instance, Q inside one of these groups. And Q has been a very hard group to embed into a finitely presented simple group, despite having solvable word problem. So from the perspective of the Boone-Higman conjecture, it's certainly a very interesting thing. And this is not possible for, say, Thompson's group V, but it would be for some of these guys, just to sort of motivate a little bit why one might be interested in these groups. So what I did was I studied these in sort of full generality, and I say that their derived subgroups are always simple. And I characterize finite generation, and the finite generation is characterized by you need your group of slopes to be generated by finitely many algebraic numbers. So it's permitted for it to be something like square root 2, but if you chose a transcendental number like pi, this would be an obstruction for finite generation. Okay. Yeah, so we also compute the homology and sort of try and comment on the classification of these groups, but I'm not sure that I would have time to fully explain this. One thing that I would say is that in computing the homology, we found out that one of these guys that comes from like an irrational number, which is called Cleary's group. So this is where you just take, instead of the group generated by 2, the group generated by the golden ratio. It's called golden ratio V by some people in the community, the irrational slope Thompson's group in some parts of the community. And it's known to be finitely presented in simple already. But what I was quite surprised by was that it's not rationally acyclic. So when you look at the homology with respect to Q, it doesn't vanish. And this is unlike any of the sort of finitely presented simple groups that we've seen before. This has been a question that was asked, like, is it possible to have a finitely presented simple group that's infinite, but is not rationally acyclic? And this construction provides examples of that. So this will come out in the next month or so. Cool. Yeah, so I in doing so, I've developed this very strange class of groupoids that give rise to a very broad class of UCT-Kirchberg algebras. And in some sense, they're coming from these left-cancellative semigroups. Is the construction. So some people had already studied some things which were developed. So one thing is, if you took finitely many integers to be your slope set, to be generating your slope set, this is like single vertex K graphs. So it's something like that. But then if you took sort of a real number, right, you could take any real number and say the group that's generated by that's going to be my slope set, a positive real number. Then you're going to get a very strange construction where you get, every time there's an integer, you'll get the Kunz algebra on that integer. And then it depends really discontinuously on this real parameter. And so this already had attracted some interest by like Carey Phillips, Putnam, and Rennie. And then its K-theory is computed by Shin
So, sorry,
at some point. Yes.
What does the term balanced mean there in that paragraph? The balanced K-theory.
Yes. Yes. Okay. So the idea is, okay, this is maybe actually slightly off. So what it's maybe what I should say is that you get the UCT Kirchberg algebras where the rank of K1 is one less than the rank of K0, or they're both infinite. So it's a very general construction. Yeah, so it's not actually quite balanced. I don't know why I say that this is balanced. No, it's the interval exchange ones that's balanced. But yeah, so I mean, it's a very strange construction. You get all of the Kunz algebras appearing. You get some things with like infinite rank K-theory appearing. And yeah, it's very interesting from this perspective of topological full groups as well.
Actually,
So,
don't the Kunz, I mean, isn't the K0, doesn't the K0 and the K1 of a graph algebra of a regular graph have the same rank? Like
oh, so maybe I do mean
sometimes,
balanced. Maybe I'm getting confused, but yeah. So wait. Yes. So I do mean that they have the same rank then. Yeah, sorry, this was exactly what confused me. So for the Kunz algebra, yeah, K1 and K0 have the same rank, yes. Sorry, yes, so it's all the UCT Kirchberg algebras where K0 and K1 have the same rank. That's what I mean. Yes. Sorry, I got a bit confused then. Cool. Yeah, so yeah, very general construction there that you can look at these papers by Shin and by Carey Phillips, Putnam, and Rennie. Okay, what time are we on? Well, we have about 5 minutes. So I can say a little something very quickly about why purely infinite things are kind of interesting. So I had this project with the Eusebio Gardea where we wanted to play a game. And the game was, so we start with a topological full group, and we want to find out, was my C-star algebra that I started with purely infinite? Just by looking at topological full group. And there is a condition that characterizes this. In fact, there's several. But one that I think is especially interesting to highlight is this condition of vigor. And the reason why is, I'm going to skip over what vigor actually is. You can ask me about this later. But it was introduced by Bleak, Elliott, and Hyde in order to investigate when simple groups are generated by two group elements. So there's this big open question whether every finitely presented simple group is generated by two group elements. And vigor was a sufficient condition to show that your group would be generated by two group elements. And this theorem is due to Blake, Elliott, and Hyde. And so this vigor condition that's to do with this weird question in combinatorial group theory actually characterizes purely infinite groupoids, which I think is kind of a really shocking interaction. If anyone's got any sort of understanding of why vigor would have anything to do with, and two generation would have anything to do with being purely infinite as a C-star algebra, you're on some, yeah, you're very smart. So this is something that I find very attractive about the field of topological full groups. You realize that sometimes you're talking about the same thing with different people and you're interested in them for completely different reasons. Like we're interested in pure infiniteness for you know, completely different reasons to why people are interested in these vigorous groups and this kind of thing. Okay, so this is my summary. So my summary is basically just to say, well, there are many people in this audience. I can see that there are many people in this audience who know very much about ample groupoids. They know a lot about maybe Cartan subalgebras, sort of dynamical systems and stuff. And because of this, they're actually very well placed to provide group theorists with new examples of groups that they might be interested in. In particular, these infinite simple groups with finiteness properties. And, you know, I really encourage people to start to think about some of this and think about, like, this is a really fun kind of field to do in. I've certainly really enjoyed thinking about this over the course of my PhD. And yeah, I think that there are many interesting open questions. So my final slide will just be on some open questions. And like, you know, as Cortinius said, I mean, there's already many interesting questions to ask about graph algebras. Like some things have been answered about them, but there's some things that we don't know. Like we don't know what kinds of groups embed into these topological full groups. That would be a very interesting thing to understand, because it's relevant to this Boone-Higman conjecture, for example. And so, yeah, I just encourage people, you know, this is topological full groups, and yeah, come and join the team, I suppose. So yeah, as promised, here are my my open questions at the end. So people in group theory, it sometimes seems that they know so much, but also at the same time, it's sometimes like, wow, there are some really easy to phrase questions that are very difficult to answer, and you would hope that a lot of these questions actually we could help people in group theory with, like this Boone-Higman conjecture. I know a lot of people in group theory that are working on this, and they very much would like people that say work in groupoid homology to help them and things like this. So yeah, that's my talk. So thank you.
So thank you very much, Owen, for a very inspiring talk. Are there any questions from the audience?
I have a question.
Yes, please go ahead.
Hi, Owen. This is a question about the C-star algebra of IE of gamma.
Yes.
Do those have unique trace?
Yes, exactly. And the image of the unique trace gives you back the subset of R.
Okay, great. And then the Elliott invariant, it's Z plus theta Z, and then Z for the K1, or Z for the K1.
Yeah, right. But I
Okay.
do this for any subgroup of R, right? So I mean, also this includes the car algebra as well. So the car algebra K, what's always true is that your K0 is going to be exactly your group gamma. Yeah,
But
like
then
as an
K1,
ordered
it's
group.
not always the same.
K1 is a little bit more complicated, but yeah, it's I have a description in my paper. It's fairly ugly. I would say it's a fairly ugly formula in some ways. One thing that is true is that the HK conjecture is true for this. So the least ugly way to describe it is in terms of the homology of this underlying group gamma, right? So you can definitely say that so K0 will be your gamma, and then your K1 is something like the sum of the odd homology groups of gamma. But like, yeah, I don't know, but it's again one of these things that you assume would be very easy in group theory, but like computing the homology of subgroups of R was actually quite a hard task, and it already looks very complicated. Yeah. Yeah. But yeah, if you want the formula, it's my only solo of the paper.
Okay,
Yeah.
I'll take a look. Thanks. Good talk.
Thank you.
Any other questions? I have a couple. So at some point you mentioned this that the Kirchberg that you got all the Kirchberg algebras with balanced K theory by some construction. Yeah.
Yes.
Are these but yeah, so balanced K theory, so you admit that the K theory not be finitely generated.
Yeah, this is not needed.
Okay, so,
So if you take,
they are not all Katsura algebras.
no. Yeah, so what I'm trying to explain in this, and I think I didn't maybe do the best job. So I describe a class of groupoids in order to get these full groups, and this class of groupoids is already a generalization of two classes of groupoids which have been studied already. So one of them is the single vertex K graphs. Mm-hmm. And the other one is this strange class of C-star algebras which have already been studied by Shin and Carey, Phillips, Putnam, and Rennie. And then they're a class of UCT Kirchberg algebras where your input is some real number. So you give them a real number and they give you a UCT Kirchberg algebra. And their construction, they had already shown that it contains all the UCT Kirchberg algebras with balanced K theory. So I'm not claiming that it was me that has this, to be clear. Yes, but this is this strange class that yeah, I'd encourage you to look at say, yeah, these papers. It's a very weird construction, I'd say. And it has very interesting like KMS structure, if I remember right. Like this was like part of the motivation as well.
And the other question is, I mean, topological full groups are can be, as you pointed out, defined by starting with a groupoid, right? Now the group has a sister, has an associated sister algebra, say reduced sister algebra, but it also has a purely algebraic algebra, like the so-called Steinberg algebra. So,
yes.
Whenever there is a theorem that says that some property of this groupoid translates into a property of the sister algebra, an algebraic property, then one can ask whether the same is true for the algebraic algebra.
Right. Yeah. And yeah, I'm aware of these yeah, these sort of things around Steinberg
So,
algebras,
for
and I'm
example,
aware,
yeah,
for instance, there is a reconstruction theorem I've read for Steinberg algebras that's similar to Renault's theorem, where you could probably just as much put C-star algebras here as something in Steinberg algebras maybe. But yes, I think that actually these Steinberg algebras and their interactions with topological full groups, I would be very interested to understand more about this. Like, for instance, it's possible that Steinberg algebras are generated algebraically by elements of your topological full groups and then certain projections, right?
mhm.
This certainly happens on the level sometimes of the groupoids. I think that would be a really interesting question to try and understand algebraically on the Steinberg algebras level. I mean, you have this canonical subgroup inside your Steinberg algebra that I think could have some interesting properties actually. But yes, that is definitely a sphere of research that I think is underdeveloped. Like, what's the relationship between topological full groups and Steinberg algebras? But I mean, Steinberg algebras, I suppose, is a relatively recent field of study, my understanding. So yes,
Yeah, one last question. So,
of course.
when you mention Sturmian subshifts,
Yes.
so there is this sister algebra defined by Toki, by Carlsen, associated to
Yes.
any subshift, and not necessarily
Yes.
finite. Blah, blah, blah. So does this sister algebra come up in what you said?
I haven't seen this
in
studied.
this.
I'm aware of this actually. Yeah. So I mean, what I would say is that so certainly this construction, this groupoid construction that Tucker has, it would give rise to groups that would be often simple, finitely generated, and infinite. And then the question is, what other properties that they have? Well, I mean, some of them would fit into, like, included in that would be these two major results, right? Like, included in that construction would be these two major results, because this is coming from Cantor minimal systems. This is coming from Cantor minimal dihedral systems. So subshift of the coming from the dihedral group, from the dihedral group. But actually, already there's some very mysterious phenomenon going on the topological full group side for Z squared subshifts. So it's very subtle, very hard. I would argue maybe hard, not so well understood, to determine the amenability of topological full groups coming from Z squared subshifts. Some of them are amenable, some of them are not amenable. There are sporadic examples. Some of them are very interesting, and but it's not like we really understand this well. And so I would say that a lot of the effort in the community of people thinking about topological full groups and subshifts, where they're focusing their efforts on, I would say, is mainly about this determining amenability for Z squared. Mm-hmm. And after that, maybe polycyclic, because a big part of that is that people would really like to know if this group is always amenable. And this is always coming from like up to some embedding thing, it's coming from a Zn subshift, I suppose.
Okay. Are there any more questions? Otherwise, I'll stop the recording here.